Hello, we are Team 3. I am Natalie.
Hello there, my name is Nolan Punama.
Hi, I'm Brandon Hill.
Hello, my name is Juan Cruz Jimenez.
Our main goal for this project was not only to set up, but also to calibrate our own systems for testing distance and temperature using the sensors and software that came in our Arduino kits. To do this, we needed to apply what we learned not only in class, but also the previous labs. For the project, we were required to build 3 systems: temperature, distance, and depth, respectively. And in order to understand how to make these systems, we were also required to go over the listed lessons. Our plan to do this project was mainly to divide up the work among the group. There were 3 systems to set up, so we divvied them up among 3 people, 1 team member each. That way we would complete the project more efficiently.
For designing and building the temperature sensor, I followed this circuit diagram, and so I just connected all these wires to the right points, 2 on the display went to the board, 2 went to the breadboard, and then as you can see on the breadboard I have those 2, and then I have several wires, a lot going from the breadboard to the breadboard, but others going from the breadboard to the Arduino board. Then also I have a 10 kilo ohm resistor and a thermoresistor, and here's the code. I didn't have to change much to the code. It displays the temperature in degrees Celsius, so I just had to convert temperature from Fahrenheit to Celsius. In calibrating the temperature sensor, I had to get 3 different points of data comparing the output of the temperature sensor on this display to a actual temperature, a measured temperature that I knew. So the first point I used was the temperature of this room that I'm in. The second, I used pieces of ice. I held 2 of them around the thermoresistor. That was the quickest way I found to cool down the thermoresistor, and that would simulate 0 degrees Celsius. Finally, the third data point I used was outside temperature. I looked at outside temperature. I took this whole setup outside, and then I waited for a bit, and then finally I put those into an Excel sheet, created a scatter plot, and then created the trend line for the scatter plot, and then found the equation, the R-squared value. I found that it's important to get as many data points as possible when calibrating, so I get the most accurate calibration possible. If I had access to a mercury thermometer or something similar, I'd be able to get a lot more, but since I did not have that, I had to rely on a low number of data points. This is potentially useful in future job or engineering applications because temperature is a very common thing to measure in engineering, and knowing how to calibrate a thermometer accurately is always important, so you get accurate temperature readings.
Setting up the equipment was relatively easy looking at the first diagram. There was only 3 wires to connect, the ground, 5 volt, and port 9. And with the second diagram, we have the ground and port A0. But with the third wire is where a small problem began to arise. The 5 volt port is already in use, so instead I used the 3.3 volt port, and the results turned out just fine and working as intended. When getting my results, the ground cable kept slipping out, so a few attempts was necessary in order to ensure proper results. Calibrating the depth sensor was very easy to do by calculating 10 data points, each increasing in depth. The minimum depth was 5 millimeters, and the maximum depth possible was 40, but my points only went from 5 to 25 millimeters. With increasing depth, we also had increasing distance traveled by the servo motor. In terms of significance, I learned that the more data points collected for calibration, the better and more accurate your resulting line will be. In general, the regression curves can be used in any field of engineering, but for the specific example of how my lesson could apply in engineering is, for example, you have a reservoir that is filled with water, and the more water in the reservoir, the more water needs to flow out. My lesson can specifically do this using the depth sensor and the servo motor, where the servo motor controls the outflow of water.
As you may see here, this is lesson 14, the ultrasonic and servo motor experiment. The sensor is connected to the Arduino, and so is the motor through the pins. These are the design steps that I've used to connect them. Lesson 11 servo and lesson 14 servo. One of the difficult parts of the experiment was actually the coding. I had to learn how to download a new library. Also, the code that was provided in web courses, the trigger pin and the echo pin, were incorrect. Instead of pin 12 and 11, which you see here, it was originally pin 2 and 3, which I had to change. So the serial that began 9600, it was actually originally, and if you see in the comment, at 115,200 baud. But I switched into 9600 because that is the generic one that would come out originally when it is clicked on the serial monitor. One of the calibration steps that I did to calibrate the tread line was to create more data points than the necessary amount. Instead of 3 data points or 10 data points, I exceeded that amount to create a more precise and accurate tread line throughout the graph. One of the great significance that I've understood in this class was to understand the sensitivity of the device, the ultrasonic sensor. Although it might skew a little bit of my data points by its sensitivity, increasing the human error, it is also a very convenient device to actually calculate, how far something is. It could be used as a device, a home device, to calculate how close an object is, or if an intruder is coming in.